An interference fit, also known as a press fit or friction fit, is a fastening between two parts which is achieved by friction after the parts are pushed together, rather than by any other means of fastening. For metal parts in particular, the friction that holds the parts together is often greatly increased by compression of one part against the other, which relies on the tensile and compressive strengths of the materials the parts are made from. Typical examples of interference fits are the press fitting of shafts into bearings or bearings into their housings and the attachment of watertight connectors to cables. An interference fit also results when pipe fittings are assembled and tightened. A press fit is also required to mount wheels on an axle to make a wheel set. Introducing interference between parts, an interference fit is generally achieved by shaping the two mating parts so that one or the other, or both, slightly deviate in size from the nominal dimension. The word interference refers to the fact that one part slightly interferes with the space that the other is taking up. For example, a shaft, or an axle, may be ground slightly oversized in the hole in the bearing, or the wheel may be ground slightly undersized. When the shaft is pressed into the bearing, or when the wheels and roller bearings are pressed onto an axle as in the case of a wheel set, the two parts interfere with each other's occupation of space. The result is that both parts elastically deform slightly to fit together, creating an extremely high force which results in extremely high friction between the parts so high that even large amounts of torque cannot turn one of them relative to the other. They are locked together and turn in unison. Tightness of fit. The tightness of fit is controlled by amount of interference. The allowance. Formulas exist to compute this allowance that will result in various strengths of fit such as loose fit, light interference fit, and interference fit. The value of the allowance depends on which material is being used, how big the parts are, and what degree of tightness is desired. Such values have already been worked out in the past for many standard applications, and they are available to engineers in the form of tables, obviating the need for re-derivation. Therefore, if a loose fit is desired for a 10-ohm shaft made of 303 stainless steel, the engineer can look up the needed allowance in a reference book or computer program, rather than using a formula to calculate it. For non-commercial parts, there are rules of thumb for steel and aluminum. For tight fits, the bore diametrical tolerances for a press fit with a rod constraint are given by subtracting 0.0001 0.0003 inches. The rod tolerance, with a bore-sized constraint, can be found by adding 1 3/10 to the given bore diameter. For slip fits, the bore diameter must be 0.0005 0.0008 inches wider than the rod. Transversely, the rod must be 0.0005 0.0008 inches under the given bore diameter. These broad guidelines save the trouble of having to calculate or look up tolerances for a single instance piece. Assembling. There are two basic methods for assembling an oversized shaft into an undersized hole, sometimes used in combination: force, thermal expansion or contraction. Force. There are at least three different terms used to describe an interference fit created via force: press fit, friction fit, and hydraulic dilation. Press fit is achieved with presses that can press the parts together with very large amounts of force. The presses are generally hydraulic, although small hand-operated presses may operate by means of the mechanical advantage supplied by a jack screw or by a gear reduction driving a rack and pinion. The amount of force applied in hydraulic presses may be anything from a few pounds for the tiniest parts to hundreds of tons for the largest parts. Often the edges of shafts and holes are chamfered. The chamfer forms a guide for the pressing movement, helping to distribute the force evenly around the circumference of the hole, to allow the compression to occur gradually instead of all at once, thus helping the pressing operation to be smoother, to be more easily controlled, and to require less power, and to assist in aligning the shaft parallel with the hole it is being pressed into. Thermal expansion or contraction. Most materials expand when heated and shrink when cooled. Enveloping parts are heated and assembled into position while hot, then allowed to cool and contract back to their former size, except for the compression that results from each interfering with the other. This is also referred to as shrink fitting. Railroad axles, wheels, and tires are typically assembled in this way. Alternatively, the enveloped part may be cooled before assembly such that it slides easily into its mating part. Upon warming, it expands and interferes. Cooling is often preferable as it is less likely than heating to change material properties, for example, assembling a hardened gear onto a shaft, where the risk exists of heating the gear too much and drawing its temper. See also, coiled spring pins, engineering fit, engineering tolerance, statistical interference, references. External links, diagram of an interference fit. Interference fitting a formulae for calculating clearance reductions when using interference fits for bearings on shafts and in housings.